The integral and p-series tests, part 2. Let's start by looking at the p-series test. So a p-series is one of the form k to infinity of 1 over n to the p, where p is some number. We already saw in the last video that 1 over n diverges. So that's a separate case. But let's look at all the other cases. We know that if p is greater than 1, then our series will converge. But if p is less than or equal to 1, then our series diverges. So why is this a true statement? Well, the proof is the integral test. So without loss of generality, let's consider the integral from 1 to infinity of 1 over x to the p, which I could rewrite as the integral from 1 to infinity of x to the negative p dx. Now, I'm not going to go through all the correct notation. This is just to get the idea of what's going on. But when we integrate, we would need to add 1 to the power and then divide by the new power, except in the case when n equals 1, but we already know that diverges. That's the special case. Now, I'm going to write this as c, some constant, times x to the negative p plus 1, because the power is what really matters. So what if my original power is greater than 1? Well, if the original power is greater than 1, the negative p plus 1 is still negative. Which means I could write the antiderivative as c over x to some positive power. What's important is that I have x with a positive power in the denominator. Because when I plug in infinity into x, I get something over infinity minus a finite number, which is 0 minus a finite number, which is finite. So if the integral converges, I know that the series converges also. But what if p is less than 1? Again, we've already taken care of when p equals 1. Well, then negative p plus 1 will be positive. And if that occurs, I will have, after the antiderivative, some number times x to a positive power that's in the numerator. Which means when I plug in x goes to infinity, I get infinity minus a finite number, which is infinity. And since the integral would diverge, the series would diverge as well. Let's look at 3 quick examples. And all we want to do is determine whether the series converge or diverge. And we might add a few more details. We'll start with the series from 1 to infinity of 1 over n squared. This is a p-series, where p equals 2, which is greater than 1. So by the p-series test, our series converges. Nice and quick. I like the p-series test. Second example. Let's look at the series from 1 to infinity of 1 over 2n. Well, I could simply write that as 1/2 times the series of 1 over n, which is a p-series. Where p equals 1, which is less than or equal to 1. Kind of a weird technicality to write, but I'll write it anyways. Which means that this series diverges by the p-series test. Our final example. Let's do the sum from 0 to infinity of 1 over 1 plus n squared. This is not a p-series. P-series have to be written as 1 over n to the p with nothing else except in cases like this where we can pull stuff outside of the summation. So I cannot do a p-series, but I can use the integral test. Let's look at the integral from 0 to infinity of 1 over 1 plus x squared dx. And I will do the technicalities here. The limit as b goes to infinity of 0 to b over 1 over 1 plus x squared dx. Let's find the antiderivative of this. Well, the antiderivative is the arctan or inverse tan of x. And if I plug in b, quote unquote, equals infinity, I get the arctan of infinity, which is pi over 2, minus the arctan of 0, which is 0, which of course is a finite number. And since the integral converges, I note that the series also converges. So we would say by the integral test, the series 1 over 1 plus n squared from 0 to infinity converges.